Okay, there's been a lot of field trips in the last few days, so I'm putting together this video so that we're ready for our test next week. Introduction to trig, we've done most of this in class, but for anyone who wants to go back and look at this, it'll be available for you on YouTube. Okay, intro to trig. Trigon stands for triangle, metron measurement, so everything here we're focused on triangles, specifically right triangles. And we're going to learn what the basic trig ratios are. And then we're going to use those ratios to either find missing sides if we know some of the angles, or if we know some of the sides and we can find missing angles. In class we did an activator, and that activator included doing a whole bunch of measurements on these triangles within triangles within triangles, and they're all right triangles. We measured all the sides, and then I asked you to actually find the quotient. Literally divide the opposite side of this angle here, in this case it was 30, some of you did 40 degrees, and find the quotient or the resulting of division here of the side opposite divided by the hypotenuse. And then we took all, and we did that, by the way, for the little triangle, the next bigger one, the next medium one, etc., etc. And then we looked at the side adjacent divided by the hypotenuse here. And then finally we looked at all of the opposite sides divided by the adjacent side here. And what did we find in every case? We found that they appeared to be constant. We would calculate out the same number here across each row. They weren't all the same number going down the column. But all of the side opposite divided by the hypotenuse, whether we had the small triangle or the big, they were constant, and the same here and the same here. So why is that? Why are they constant? Well, it starts with the relationship of similarity. So remember, back earlier in the year, if we have an angle here, and this angle reflexive property is equal to itself, and we have a triangle within a triangle. In this case, our triangles were labeled with an angle that is right, and we know all right angles are equal to 90 degrees, and they are congruent. So the converse of the corresponding angles theorem would say that if you have corresponding angles that are congruent, these lines must be parallel. And either by third angle theorem or by corresponding angle postulate, these angles here must also be congruent. And so by angle, actually I like to say angle, we can say that the triangles are similar. And of course, as we said on the previous page, these ratios, opposite divided by hypotenuse, adjacent divided by hypotenuse, and opposite divided by adjacent, they all appeared to be constant. Each one, didn't matter the size of the triangle, for a given angle, they all appear to be constant. And why is that? Well, it comes straight from this similarity relationship. So let's draw triangle. I'm going to call this side A, B, C, D, and E and F. We know that because they are similar, that the sides are proportional. So A is to B as C is to D as E is to F. And we did a lot of work on that relationship earlier in the year. Well, let's just focus on this opposite divided by hypotenuse. For the small triangle, right here to my left, this triangle, if I look at this given angle here, theta, the small triangle, the side opposite theta in the small triangle is E, and the hypotenuse is C. So I'm substituting now E over C. And if I look at the large triangle, the side opposite that angle theta over the hypotenuse is, we've got F divided by D. And what we observed and calculated in our measurements is that E divided by C appears to always be constant to F divided by D. And the reason for that comes straight out of this proportion here. So if I cross multiply here, then CF equals DE. And if I divide both sides here by CD, which I can do, I can divide by anything I want to as long as I do it to the other side, then my C's cancel and my D's cancel. So I end up with F over D equals E over C. And that's exactly what we observed in our measurements. So I could do this exact same algebraic exercise for the adjacent over hypotenuse and the opposite over adjacent, and find that it's not by coincidence that these are constant. It's purely algebra stemming from the proportional relationship to these sides. Okay, in math, we like to name things that are constant, just like we name pi, standing for 3.14, etc., etc. And we've got more constants that we use in math. Well, here we've named this relationship of the opposite side of a given angle divided by the hypotenuse. We've named it the sine of that angle. That's a hard I sound. We've named the adjacent side divided by hypotenuse the cosine. And we've named the opposite side of a given angle divided by the adjacent side the tangent of that angle. So these may look complicated, but they're pretty simple concepts. If we have a given angle in a right triangle, and here is theta, I'm just going to write theta, how it's spelled phonically. If we have this angle, then the side opposite would go directly here, and that's everything is from the perspective of that angle. The hypotenuse, of course, is always opposite the 90 degrees. And then, by process of elimination, the other side is called the adjacent side to that angle theta. And so you can see here that these are our three basic trig ratios that we're going to use. And we're going to have a little mnemonic, almost like PEMDAS or Please Excuse My Dear Aunt Sally. The way we memorize these, and you must memorize them, is SOHCAHTOA. This is how most students memorize these. SOHCAHTOA. It's a little bit catchy, and the S stands for sine, and the C stands for cosine, and the T stands for tangent. And you can see here SOHCAHTOA. This is a memory that the sine of a given angle is the opposite divided by hypotenuse, adjacent divided by hypotenuse, opposite divided by adjacent. And so we use this mnemonic to memorize these ratios. Now, in math, we always need a way to undo any operation that we perform. For instance, we undo addition with subtraction, we undo division with multiplication, we undo square rooting with squaring. Well, we need an undo, an inverse operation of sine, cosine, and tangent. And we need these because that's how we would eventually solve equations that involve these functions. And so the way we notate that is with what appears to be a negative exponent, but it is not. It has nothing to do with exponents, in fact. This is just the notation for undoing the sine. So we would perform this sine of a given angle is really just the side lengths here, as noted, the quotient, the resulting quotient. And if we wanted to take those sides, opposite divided by hypotenuse, and go in the opposite direction, then we would do an inverse sine, and we would get back the angle. Now, what am I talking about here? Next page, what I mean. So we have already said that these are constant. For a given angle, the opposite side divided by the hypotenuse is a constant. Well, all of this math has already been done. All the measurements and all the quotients have already been found for us and have been in use for really thousands of years. And here is, they're listed in an abridged trig table, it's called. And so down on the first column is a degree particular angle, and it would be followed by the sine and the cosine and the tangent. The sine is the opposite side divided by the hypotenuse. So this column is the result of that quotient. And cosine is the adjacent divided by the hypotenuse, and that's its quotient, and the opposite over adjacent is the tangent. So in my day, we would just look up a particular angle. Say I was doing something with 12 degrees and I wanted to figure out some missing sides. Then I would look up what the resulting ratio, quotient of the ratio is here, for instance sine, and I would use that number. Well, all of these numbers have been stored this as a giant lookup table, the calculator. And I know you've looked at these buttons for a long time on your calculator. You're probably, well, I'm sure you've never known what they are, but all they're really doing is just accessing that lookup table on the previous page, the trig tables, and retrieving that number for you, because that table is located on the microprocessor, the calculator, stored there, and it's just accessing that information and retrieving it for you. So for example, here's the sine, cosine, and tangent buttons on the TI calculators that we use in class. If I wanted to know for 25 degrees here what the opposite side divided by the hypotenuse would equal for a 25-degree angle within a right triangle, then I would hit the sine button, push the sine button, and then I would input 25 degrees, and I would hit the equal sign here, and then I would retrieve this number from the lookup table. And since most of you, as we talked about in class, are using iPhones, or some of you are using Galaxy or Android, it's important that you know the personality of your calculator. The iPhone tends to use what's called reverse Polish entry system, and so on those calculators you've got to be careful. You're going to enter the 25 degrees first and then push the sine button. I believe the Android would be exactly that. Its calculator would be just like this TI one, and the Galaxy I think is like the iPhone, but I'm not 100% sure on that. So here we can find, just by accessing that lookup table for 25 degrees, this ratio, and we can use that ratio to find missing sides of that right triangle. Now what if we wanted to get the angle? What if we knew the two sides, the opposite divided by the hypotenuse, and we wanted to get back this angle? So what if we knew this, but we didn't know the 25 degrees? That's when we would use the inverse function. And the inverse functions are usually always right above the buttons on the calculator. So you would access them using the second button. And here we would do inverse sine, and we would input the actual, we'd either put in the sides here if we wanted to do that division, or if we knew this ratio, we can put that in there, 4226, and hit the equal sign, and you will get back, if you do 4226, you'll get back something very close to 25 degrees. On the TI calculator, you'll get something like this. And that just goes to show you just how sensitive these ratios are. So it's important that you use a fair amount of digits of accuracy here in the ratio if you're going to retrieve back the angles. Okay, so keep that in mind. All right, let's see how this works now. So we have a right triangle. It's a 30, 60, 90, which we already know a lot about because we did special right triangles, but let's pretend we don't. From the perspective of the 30 degrees, x is opposite. And of course, the 40 degrees is the hypotenuse, always across the 90 degrees. So by process of elimination, y is adjacent. So katoa. This is our memory jogger that we're always going to use. And we want to know x. So we want to know the opposite. Here's where the opposite is located. Opposite is in the sine ratio as well as the tangent, and we know the hypotenuse. So this is what we know. Well, out of the three ratios, only the sine has all the information that we need. So we have only that to go on. So we've got sine of theta equals opposite divided by the hypotenuse. The sine of 30 degrees equals the opposite, which is x, divided by the hypotenuse, which is 40. To solve this, we're basically multiplying both sides by 40, which is where cross multiplication arises from. So we've got 40 times the sine of 30 equals x. And on the TI calculators, you're going to go ahead and take the sine of 30 degrees, and then you can multiply that by 40. The sine of 30 degrees is a half, and multiplied by 40, of course, is 20. And we knew that was going to be the case, because on a 30, 60, 90, the short side here is half the length of the hypotenuse. So we knew we would get 20. But here's just an example on how to use the ratios. Now let's find y. Well, y is, I'm going to erase this so we can reuse this again. Y is adjacent, so we have a here, and the hypotenuse we know, but we also did just solve the opposite, so we have our choice. We could use cosine or tangent, and I think it's a good idea if you try both. So let's say cosine of an angle, theta, equals the adjacent divided by the hypotenuse. Cosine of 30 degrees equals the adjacent, which is y, divided by 40. Again, we're going to cross multiply up, and we have 40 times the cosine of 30 equals y. And we're going to go ahead and find the cosine of 30 and multiply that by 40. And y is approximately 34.6. Now, remember on the iPhones, you're going to enter 30 first and then hit the cosine button. That's the reverse Polish. And let's compare this to using the tangent. I said we could use both. So we've got tangent of theta equals the opposite divided by adjacent. The tangent of 30 degrees equals the opposite, which we solved for, is 20. And that equals 20 divided by the adjacent, which is y. Now we're going to cross multiply that up, and we end up with y times the tangent of 30 equals 20. Well, we want to get y all by itself, and y is being multiplied by the tangent of 30. Remember, the tangent of 30, although it might look complicated, it's just a number. So we want to undo that multiplication with division. And whatever you do on one side, you got to do on the other. So these cancel, and we end up with y equals 20 divided by the tangent of 30. And we can solve for that now. Take the tangent of 30, and we get exactly the same answer as you would expect. So this is just an example of how the ratios are very related to each other, and you've got multiple opportunities or options sometimes within a given problem. Now the last examples here that we're looking at are trying to use the inverse functions to get the angle. This time we know two sides, but we don't know the angle. And so katoa. Always while we're practicing here. So from the perspective of z, the angle, we know the opposite and we know the hypotenuse. By process of elimination, y is adjacent. So opposite and the hypotenuse, again it's sine, and we are looking to get the angle, so we're actually going to be using the inverse sign. So the inverse function of the opposite divided by the hypotenuse is going to equal my angle, theta. So the inverse of 40 divided by 60 equals theta. And you're going to take that inverse. So 40 divided by 60. And the inverse function is retrieved at the button above, the function above. So generally you're using the inverse. I'm sorry, the second button. And here the theta turns out to be about 41.8 degrees. Now, the iPhone users and some of the Galaxy, I think, products, they have a separate button that you would use for the inverse functions. And I think sometimes they're just called like a sine. That would be the inverse sine. Okay, this is what you want. You may see this on your calculator. It's got an H. This is what you don't want. We're not going to use those functions at all this year. All right, now moving over to finding y. Well, obviously, the easiest thing to do would be to use the Pythagorean theorem. We know 2 out of the 3 sides of a right triangle. We can easily solve for y. But let's practice up using one of the trig functions. So we've got y, which is adjacent. So we're looking at either cosine or tangent. And we have our choice because we know both the opposite and we know the hypotenuse. So you choose. I think I'm going to choose tangent, but you could use cosine. So the tangent of theta equals the opposite divided by the adjacent. Tangent of 41.8 degrees. And definitely don't put 42 and don't put 41. We need accuracy here. Is the opposite 40 divided by the adjacent, which is y. I'm going to cross multiply that up, and I end up with y times tangent of 41.8 equals 40. And to isolate y, I'm going to divide both sides by the tangent here of 41.8 degrees. Those cancel, and we end up with y equals, and you can calculate this out. We have 44.7, I guess, feet. And a few elaboration questions. What happens if we divide sine by cosine of theta? Well, sine of theta, of course, is SOHCAHTOA, opposite divided by hypotenuse, and the cosine is adjacent divided by hypotenuse. So let's actually divide these. Well, when you divide by a fraction, it's the same thing as multiplying that numerator by the reciprocal of that fraction. And you can see here then that the hypotenuses reduce out to 1, so we end up with opposite divided by adjacent, which is the tangent of theta. So tangent of theta equals the sine of theta divided by cosine of theta. Is it possible for the sine of theta to be greater than 1? Why or why not? It is not possible. It is not possible. If we have theta here and we're looking at the opposite divided by the hypotenuse, which is what sine is, the hypotenuse is the longest side of the triangle. So this isn't going to work. Always the ratio of the opposite divided by the hypotenuse is going to be less than 1. And number 7, is it possible for cosine to be greater than 1? No, it's not. Neither of these are possible for the same reason. In this case, cosine is adjacent divided by hypotenuse, but the hypotenuse is the longest side, so this ratio is also going to be less than 1. And finally, is it possible for tangent? Well, it is, because you have a side A or B. You don't know if is B greater than A, is A greater than B, depending on the triangle. Either scenario is possible. So it's certainly possible for tangent of theta to be less than 1 and greater than 1. So we can put this here, less than 1 and greater than 1. That is possible. And I might as well just go ahead and put this up here just as a conclusion. Okay, I hope this helps, and thanks for listening.